Awesome. Thank you for coming back. I knew it will be difficult to bring you back from the other room, but we have a very interesting panel, next panel of the day. Donc, merci d'être de retour. Alors, il est maintenant temps de présenter une personnalité qui n'a pas besoin d'être présentée, professeur Normand Mousseau, professeur de physique à l'Université de Montréal, directeur scientifique de l'Institut d'énergie Trottier et co-directeur scientifique du Carrefour de modélisation énergétique. Son travail ne s'arrête pas là, il est aussi cofondateur de l'accélérateur de transition et membre fondateur de l'Institut climatique du Canada. Aujourd'hui, Normand va être le modérateur de notre deuxième session, Résilience et adaptation dans la modélisation énergétique. J'aimerais qu'on accueille chaleureusement Normand sur la scène. Merci.
Merci beaucoup. Alors, en effet, donc un petit rappel, il y a de la place en avant, donc ceux qui sont un peu tassés à l'arrière, venez et vous verrez nos conférenciers de manière beaucoup plus claire. Donc, je voudrais accueillir les conférenciers. Let's have the speakers. Scott Barfield McGuinness, Antoine Rousy qu'on accueille à distance et Antoine Lesage-Landry. Donc, chacun comme le même format que précédent. So we'll first ask Scott Barfield, who is Principal Technical Advisor at the North American Electric Reliability Corporation, NERC, to start this panel. Scott.
Thank you, Namorn. So evolving transmission planning and modeling for those uncertainties, expectations that we have. Yeah. All right, so most of you may know about the North American Electric Reliability Corporation, or what we call NERC. It's to assure the reliability of the North American grid. That's our key focus. We cover North America, obviously the United States, but also Canada, as well as Baja Norte in Mexico. Those that apply to NERC are the owners, operators, and users of the bulk power system. And also, NERC was certified by the Federal Energy Regulatory Commission as the Electric Reliability Organization, another acronym that we use called the ERO. And as a part of that, even though we're in the United States, NERC has memorandums of understanding with the Canadian provincial authorities. That way we also can operate and do business in Canada. Four of the key things that we have statutorily, we're required to do these things as a part of our mandate from FERC, but also in our rules of procedure, is to educate, train, and certify personnel. We also have to, more importantly, establish reliability standards, and NERC is probably most well known for the standards that are written to operate the bulk power system and the plan for the bulk power system. When those standards are written, we're also charged with the compliance and enforcement. We do that through 6 regional entities that have a relationship with all the power companies out there. And then lastly, one of the things that we also do are do analysis and assessments. That is required for us. We have to do these things and report our findings as an independent party. From an analysis standpoint, that's a backward look. We look backward into time at how the bulk power system actually performed. Most notably, our popular report is called the State of Reliability. It comes out every year. And some of the things that it noted this past year is the fact that conventional generation, specifically the weighted equivalent forced outage rate, has gotten a little bit worse. It's ticked up a little bit from prior years, not severely, but it's stepped up a little bit. We want to pay attention to that. Solar or photovoltaic resources continue to give us problems. It's continent-wide. They trip off when you don't want them to, they can't ride through faults, and a lot of the parameters that are being used are just not correct. And then on top of that, you have security threats that are getting greater and greater every single day. Coming from world actors, adversaries, it's something that's hidden, someone we don't know. It's very hard to plan for. On a better note, transmission system reliability has actually gotten better. It's actually performed much better over prior years. And this operation of protection and control systems has also declined year over year for the last 5 years. That's important. One of the things that the State of Reliability Report also highlighted was the fact that data is key to modeling and planning the bulk power system. You have to know what data to use to get those complexities and uncertainties addressed. The assessment component, that's actually forward-looking. We have 4 key assessments that we do every year. First one is the case quality metrics. Most of you probably haven't heard about those unless you actually do planning. And what those are is an assessment of the actual models that transmission planners use to model the system. The goal of those is to reveal where particular models don't have the proper component models. For example, the photovoltaic resource is not modeled correctly, it's not parameterized correctly to make either the model converge or even get realistic results of what the expected behavior would be. The next 2 are seasonal assessments. Those look at either the summer or the winter. And actually, winter just came out last month, so it's very fresh. And then our annual assessment, which is what a lot of your policymakers look at, as well as our regions, in terms of the performance that would be expected over the next long term, the next few years out to 10 years. Long-term reliability assessment does have a couple of goals in particular. It's to make sure that the bulk power system can continually to operate reliably, but also identify those trends in demands, loads, energy, and all the things that is necessary to make sure that the system's reliable. Also to identify emerging reliability concerns. Where are the problems? Is it weather related? Is it resource related? Is it operations or planning? A key component of the LTRA, or their long-term reliability assessment, is to inform not just the users, owners, and operators of the bulk power system, but also policymakers, in addition to general public. We heard a little bit about policies that are going on now at net zero, a lot of the things that have to happen there, and that's part of that report helps show what's actually happening. And then one of the key things, along with the data that is needed to do planning and analysis, is the SOR, or the State of Reliability Report, actually helping NERC understand that data is important to managing and planning these things. To give an example, we've been collecting resource data for traditional thermal type resources for years. It's called the GAD system, or the Generator Availability Data System. We now have GADS wind systems, and GADS solar. Included within the SOR is the regional planning components, and that's to make sure the regional areas are performing at a smaller, more granular level, not just the bulk power system across North America. Summary assessments for each of those areas are included. There are a lot of graphs, really good information, charts, and also the focus is to look for emerging type issues. It's a forward-looking assessment. We want to make sure that we can identify things before they actually get bad or severe. And it's also to help us understand what the particular planning regions are doing to ensure reliability for their particular areas. What is the current situation? I think we heard from the first 3 speakers, not very good, not just for getting net zero, but for reliability as well. Resources are changing considerably. Thermal plants are being retired. Inverter-based resources are coming on very strong. A lot of incentives in that area. In fact, the trajectory is kind of crazy when you look at it. Climate is creating a lot of problems for us. Wildfires in California, freezing weather in Texas, hurricanes in the southeast United States, as well as coming as far up in the northeast as well. And the ongoing retirement of thermal resources and large synchronous machines. May not seem like much. From a net zero standpoint, that's okay. We want to get rid of the fossil plants, right? But the problem is we're also losing system strength, short circuit ratio, the ability to clear faults and have protection and control systems to work correctly. And that's very important. We've heard a little bit about the electrification of loads, transitioning from fossil heating to heat pumps or electric loads. Electric vehicles are coming along. All those change the dynamics, not to mention the consumer behavior that goes along with it. There's increased interdependency between sectors. Water or municipal water systems, for example. Thermal plants need deionized water to operate. If that system's disrupted, that plant's affected. Communications, fiber line goes down, microwave system goes down, you may lose your telemetry or your communications between the substation or the plant or a control center. That's important. Just-in-time fuels, natural gas pipelines, it's also an interdependency, but it's also what supplies the resource. If that's disrupted, that becomes a problem. That could be mechanical, could be an adversary. Cyber and physical threats on the rise, and a lot of ballistic type events that go on. We have the EISEC at NERC, the Electric Sector Information and Sharing Group. If you're a utility and not a part of that, I highly recommend you join. And then we have the regulatory policy drivers that go on. The net zero, one key thing. Changing of fossil fuel heat to electric is another, but also the tax incentives and things that go along with trying to push renewables. To characterize those risks, we have a risk issue steering committee, or I don't know why I came up with the acronym RISK, basically the same thing. Every year they publish a priorities report. In the last, 4 reports, they had 4 categories. Grid transformation, which is the inverters, security concerns or security risk, natural extreme weather, and then physical infrastructure protection. This year, they created a category called energy policy or regulatory policy. That's a risk. Things we have to plan for because the actions taken today will kick in maybe 1-2 years later, but more than likely 10 years later. Still have a little bit of time to do the planning. But more importantly, from a modeling standpoint and planning, we have an issue with understanding what are the tools that we need, what are the inputs, what kind of methods should we use. Traditional planning is just not working. As our CEO or Chief Executive Officer Jim Robb would say, it's not our grandfather's electric system, or depending on who you are, maybe your great-grandfather's or grandparents' system. You can't simply do physical planning anymore. You have to account for the behaviors, the complexities and the uncertainties, as well as the inverter-based type resources that are control-based. They don't work on physics. Resource variability, we heard about that again this morning. Wind and solar, those only happen when they want to, basically. You can forecast them, but you can't dispatch them. And then constrained resources. You may have issues where you need to curtail wind, as you heard earlier. Or you may have an issue that a cyber attack has occurred. Colonial Pipeline, it wasn't a natural gas pipeline, it was a petroleum one, but that could have had devastating ripple effect across the US and Canada. And also making sure that you can transfer that energy that's produced across the network. Most of the renewables, particular wind, is in the center of the United States and the continent through Canada. Solar is out on the west, in the very south. Some in the east is starting to develop little smaller type systems. But how do you get those from the center of the continent to the coast where the load is? You've got to be able to transfer the energy. And then the historical or traditional system modeling is just not accurate enough and not capable of doing what needs to be done. To name one, electromagnetic transient modeling. Inverter-based resources, you need to be able to model at a much greater granularity to make sure they'll behave the way you think they will when there's a problem in the system. Also, modeling criteria. Is a one event in 10 years still okay? I don't know. That's a discussion that has to happen. And also extreme scenarios. That's one that's really plaguing us right now. An extreme, it can be extreme weather, but it can be anything not studied today. Traditionally, we do N-1 or multi-contingency. That's in a perfect world. You have a system, one thing happens, you're still okay. 2 things, still okay, that's fine. Extreme, but what happens when you add super high demand over what you forecasted with no wind and an adversary attacking you on the physical side or the cyber side? You got to be able to understand the complexities there and the uncertainties and have the power to be able to do the computations. Also accounting for all of the other weather components that go along with that, as well as your reserve margins. One of the things New Brunswick is talking about, you got to be able to hit that winter peak. This particular slide came out of the winter reliability assessment. I picked it because, not to highlight that there's a big red spot in Canada, but the fact that if you look over on the legend, the red is extreme weather. That's a concern, it's a risk. It's just highlighting that extreme weather could pose a concern there based on the information that was supplied. The vast majority of the United States has orange, it's elevated, but then just below the Maritimes, which is part of New Brunswick, is kind of the New England area. there's a gas risk, there's an interdependency risk there. Not that it's disrupted, but it could be curtailed because of heating homes. So those are the things we're trying to make sure all our maps are this nice gray color. Maybe it'll happen one day, maybe not, who knows. But how is NERC responding to all of this? Obviously, we're developing standards, among doing assessments and other work. More importantly, distributed energy resources, we define those down in the distribution world, not the bulk power system. We're making certain that transmission planners take into account and explicitly model those resources in their particular models. So now it's a whole nother world of information that has to be pulled in, another input. And also making sure that those distributed energy resources are parameterized correctly. Make sure those models match the devices out there and get pulled in correctly. Extreme scenarios is another big one. The Federal Energy Regulatory Commission directed NERC earlier this year to do a standard on heat and cold weather scenarios in planning. It was actually one we were in the process of working, so it came out a little ahead of schedule, but we pulled it out of what we were doing and we went with 3 additional ones, which included the natural events, which could be droughts, hurricanes, fires, cloud cover, ash, to name a few. It could be all these other things that create problems for solar, for wind, or whatever it is, transmission systems. But also gas and electric interdependency. We wanted to make sure that we covered the cross-domain type issues. In fact, we're doing another gas study to determine what the impacts of disruptions are. And then distributed energy resources, making sure that the planners understand the extremes that those things can create down in the distribution world and how the transmission and distribution interface gets affected at the bulk power level. Cyber-informed planning is actually coming. We were hoping to include this in the near term. Hopefully, probably this week, we're going to see some more information about this come out. Cyber-informed planning will actually come out sometime early next year after the industry pilot studies are completed. We decided to kind of wait for some additional information to come in. And then there's electromagnetic transient studies being done, or at least incorporated into the planning world. The non-modeling things I added in here for really the main reason is disturbance monitoring only occurs at very large synchronous machines. That's the way or the method the standard is developed. We have no visibility down at the IBR level, the very low system strength type devices. That work is currently going to include all of the IBR systems. Also, event reporting. We do misoperation reporting for protection and control systems. Companies have to figure out how to fix the problems. When inverter-based resources trip off for no reason, most operators push the start button and go on again. No, you need to figure out what caused that problem. Was it voltage related, current related, a parameter missing? What was the problem? The standard will address that. And also, NERC is proposing to register inverter-based resources that are less than 75 MVA once we've had, and also connected to the grid at 100 kV and higher. We're lowering that threshold down to 20. So any inverter-based resource out there that's greater than 20 MVA and connected at a voltage 60 kV and higher will be required to register with NERC and become subject to the reliability standards. And one that's not on here is the interregional transfer capability study. Oops, went backwards. And that's to study the ability for the transmission network to transfer energy. And that was mandated by the United States Congress to talk about that. I basically ran out of room on the slide, but this slide actually shows all of those projects and all of the work we're doing in the planning and modeling arena. I won't go through it individually because it's busy, but hopefully you can look at it after the fact. The key point is to show you that these projects don't overlap. They actually complement each other. There's specific categories that they actually pertain to, but then there's the energy component. Then there's what kind of model does it use? Is it network or probabilistic? And then what time period does it operate in? What time period are they focused on? Operations, less than a year, short-term 1 to 5 years, long-term 6 to 10 years, or even further. And also whether a corrective action plan or CAP is required to address the issue. I've also included the footnotes and the links. Hopefully that'll be helpful. And I tested them, they work. How do we close the gaps? What opportunities do we have? We heard earlier, probabilistic tools, Monte Carlo, Those do probably fit the picture, but how? How do you work those or integrate those into a physical type planning network modeling scenario? And also determine when you stop using a particular tool and transfer. How do you bring the two together? Tools also include distribution system impacts for distributed energy. That's a whole nother area. That's an area we've never really paid attention to. We want to make sure we understand the behavior and electrification in that area. Consumers are going to really drive a lot of what goes on in that particular area. And then unwinding the complexities of when you do models, when you're talking about these extreme bookends, that's a lot of models. I know the planners are out there cringing going, I need to double my workforce just to be able to run these, not to mention the computing power. Be able to process all these multi-dimensions. A lot of stuff out there. And then also making sure you have the right inputs. Those assessments feed into that to make sure that we have the information that we need to do the modeling, but making sure they're the right things. Measure it so that you know you're getting the right results that will be reality, that will be how the system actually behaves or is expected to behave. And then making sure we understand how to balance capacity planning with energy planning, how to make sure the transmission system can actually transfer the energy, whether it's an export or an import, either way. And then plan for the extreme conditions. That's what we're faced with today. Thank you for your time, and I look forward to hearing the other speakers.
Thank you, Scott. Merci. Prochain conférencier, Antoine Raosi, who is professor at the Norwegian University of Science and Technology. He should join us by Zoom, if I'm not mistaken. Ah, you're there.
Yep.
So
Yep.
you have welcome, and you have 20 minutes.
Yep. So can I? Yeah. So first of all, I would like to thank the organizer to give me the opportunity to present this work, which is it's a work I'm doing with colleagues, mostly from France and China, for now 3 years, something like this, on what we call systemic digital twins. And it's all about modeling and simulation for making strategic decisions. So this work is both done at university on my side, but we also created a company called Systemic Intelligence, and which is in charge of developing the technology I'm going to speak about. So the starting point of all of that was the COVID crisis. With a bunch of colleagues from France, China, and Singapore in the US, we wondered how systems engineering could help, systems engineering and simulation, computer simulation, could help to make better decisions in crises like the COVID crisis. And we thought that systems engineering with this holistic vision that takes into account many aspects of the problem at once can be useful. And we wrote a paper about that, but after having written this paper, we wanted to make things more concrete, and this has been the starting point of the work we're going to present now. So clearly, well, this is well known of all of you, but just for the sake of being on the same line, it's very clear that industry, in a broad sense, has to manage more and more complexity today. And one of the issues is indeed that many aspects of operation have to be taken into account from political, social, technological, legal, environmental constraints. And to make right decision, we have to put everything together. So we are convinced that we need this holistic approach that combines everything in a way. And so that's having these different aspects to take into account is one indeed huge source of complexity. Another one is that, and I think that typically the previous talk was really about that, is that we have to take into account things at different scale, a different level of abstraction. That is that to make right decision, we have to have say helicopter view in with some aspect, but this helicopter view needs also to be fitted by more concrete, more detailed data and models and everything. So what we wanted to do, in a word, was to try to propose an approach and the tool, the technology to do that efficiently. So a typical example of what we are doing is something I'm doing with one of my master students at the moment, is to try to optimize the development of an offshore wind farm on the coast of Norway. So this is typically to optimize such a deployment is indeed a complex problem and really an holistic problem, because you need to make technological choices. You need to take into account the subcontractor capacities. There is a lot of data from the field you have to take into account, of course, economical data, regulation, and so on and so forth. So what we expect to do with models is really to assess key performance indicators and to play what-if scenarios. So these indicators can be the deployment time, can be the how long do you need different support vessels, what will be the cost of the whole operation, safety issues. And all of that has to be assessed in a highly uncertain environment. And you have to take into account all these uncertainties. And typically, as you probably know, the weather here in Norway, in winter especially, can be rather tough. And so that means that if you are deploying your wind farm in this season, typically, or if you are forced to go up to this season to deploy your wind farm, then you have to really to take into account weather forecast, whether it's wind force and direction or wave heights and etc. And for that, you have only, say, probability distribution. So the models we are discussing are probabilistic in essence. All right, so as I say, the issue is really in a way to be sure to make the right decision and at strategic level. So I won't come back on that. So our idea is that we should really develop, and what we propose is to develop what we call systemic digital twins. That is, well, you probably have heard a lot about digital twin, but if you look the literature and what is on the web on digital twin is mostly a very physical vision of the digital twin. That is that you really see a lot of, say, 3D mockups with possibly some dynamics, but it's mostly a physical modeling. So what we propose is a really different approach, and what we propose is really to have a digital twin that focuses on functional aspect, on capacities, on models and data that assess the capacities you need and you will provide with your system, and to do that using really systems engineering, enterprise architecture, behavioral approaches, and things like this. So that's really the idea, to concentrate at this functional or capacity level and to propose solution for that. So really the key point here is really to deploy fully the systems engineering approach, to have this holistic approach, to try to take everything into account, of course, at a high level of abstraction. That's the price to pay to take everything into account to have this holistic approach. But we think that for many strategic decisions, it's not necessary to go into too much detail, or at least we should connect the detailed model with high-level model that help to make the strategic decision. So we should integrate in a way the say lower level model with this high-level model system that comes from systems engineering. So that's basically what we propose to do. So the technology we are developing is called WorldLab, and it's based on the modeling language that I will call that I will detail in a moment. So the modeling language is called Sigma. It's a fully formal modeling language, and what we are developing is a whole technology around this modeling language. And so that means that the environment integrates data. It's very important, technical data, environmental data, and etc. Libraries of, say, on-the-shelf modeling components that you can reuse to develop your model, and all the tools to simulate the model, to also to make Monte Carlo simulation. I will come back on that. And from the virtual experiment, computational experiment you perform on the model, to do all the data analysis to look at the results of your experiment. And the global idea of WorldLab, but again I will come back shortly on that, is to have all these things integrated together into what we call a systemic digital twin. So basically, I will not describe the Sigma modeling language, but what is key here is that Sigma is a formal language. That is, that it has a very clear, defined mathematical semantics. That is, that all operation you are doing with Sigma, they have a mathematical justification. And we use also all of the techniques of systems say software engineering to make it a powerful language. That is, it's an object-oriented language technically. But I want to present you what we call the Sigma ontology. That is, what is at the core of Sigma modeling. And basically, if you take a system, whether it's an energy system or any type of system, the idea is, what do you need to describe the behavior of this system? And so what we say is that in Sigma is that we need basically three things. The first one is that a system is a network of components. That is, it's a hierarchy of system, subsystem, subsystem, and so on. So the first thing you need is to decompose your system into a hierarchy of subsystems. And then you need, as you want to describe the dynamic behavior of your system, you need to describe what is the state of my system at time t, right? And to do that, basically, you need to describe the state of the system. And the way you describe the state of the system in Sigma is that you describe what are the stocks at time t. So here, stocks is to be taken in a very broad sense. It can be stock of matters, of energy, of information, and it can be either money, of course. It can be either say quantitative numbers, but it can be also qualitative, like is this crane working or not, or is this power station working or not, or is it in degraded state, things like this. So first thing, hierarchy of subsystem. Second thing, describing the state of the system by means of stocks. And the third thing is, now, okay, any system has a dynamic behavior. So what makes the state of the system change over the time? And the way we describe that, how the system evolves, if you will, is by describing activities. So we see systems as subsystems as actors that are performing activities. And actually, an activity starts in certain condition. It needs to book a certain number of resources to be performed. It has a certain duration. And at the end of the activity, the state of the system changes. So that's basically what is at core of the whole technology, this idea of hierarchical decomposition, stocks, and activities. And actually, it took us a lot of time to put things in such simple way, but this framework is very simple but very powerful. It turns out that is very powerful. It's also very powerful because we designed Sigma so that data, operational data, can be easily integrated into models. And especially we use this operational data to tackle the uncertainties. So typically by embedding into the model the probability distribution. So probability distribution that can be really obtained either by, say, usual parametric distribution, or by just looking at the field data and embedding that into model. So once we have designed a model or a series of models, we can, the technology make it possible to do interactive simulation and to design, say, dedicated graphical user interfaces so that it's easy for expert of the domain, but, well, in general, not expert of the simulation, but expert of the domain to visualize what's going on. And the technology we propose is really, I mean, that for interactive simulation is really like, if you will, video player. You can go forth and back in the simulation and make different hypotheses and etc. So it's like a video player, except that there are several views on the systems. So you can look at different aspects of your system. And as we wanted to be efficient again in the modeling process, we designed also a small language that helps to design this graphical user interface so that this type of interfaces are easily developed and quickly developed. But of course, interactive simulation is not enough. So what we are doing is we couple interactive simulation with classical Monte Carlo simulation or stochastic simulation, if you will. But beyond that, with optimization procedures that we call proof script. So really the idea is that in the technology, we embed a script that describe what calculation should be done and how this calculation may be chained so to obtain, so to play what-if scenarios and to typically raise systemic alerts if, say, the probability that something bad is getting too high. So we are currently developing this technology. We have already a number of partners and clients, if I may say so, but partners. I put some on my slide. So at the moment, we are really in, say, two fields. The first one is really strategic planning. So for instance, if I take the Dunkirk port, which with whom we worked, the harbor of Dunkirk in France is a coal harbor, and they are moving to a container harbor, and they want to understand what will be the impact on their infrastructure, how they should modify the infrastructure, and at which pace they need to modify the infrastructure so to make this transformation efficient. So this is typically the what we are doing with this the technology I developed. Well, we developed, and also we have other partners there, including some partners on industrial risk assessment, which is more the topic of this session. Yeah, so this is basically what I wanted to tell you quickly. So here's my contact, and yeah, that's basically it. Thanks for listening to me.
Thank you, Antoine. Et le dernier présentateur ce matin sera Antoine Lesage-Landry, qui est professeur adjoint à Polytechnique Montréal.
Merci, Normand. So hi, everyone. So I did not think about it, so I prepare a presentation in English, which is by default, but feel free to ask questions in French. So I'll be talking about, so we'll be digging into modeling steps now. So I'll be talking about the model. But of course, I want to acknowledge some of the folks that work with me on this project. So two of my students, Feng and Elodie, and also one of my colleagues that is now visiting the Hong Kong Polytechnic, Yulan Koshar, that also work on the project. So we've been discussing the whole morning, and we'll continue this afternoon and tomorrow about modeling, energy modeling. Stochastic modeling has been named quite a few times as well. We're preparing for decision-making under uncertainty, but one thing I want to add and argue for in this case is we want not only models, not only stochastic model, but computationally efficient model so that they can really be used by planners and operators. What I mean here is we want to be able to build one trajectory, another trajectory, and so on and so forth repetitively, and do not have to hire the whole of AWS infrastructure. We want to be able to run it on our local computer and test a lot of scenarios so that we can also later on embed it in a decision-making tool. So let's get into the specifics, and I'll illustrate that with a specific example. I'll talk about distribution grid because we talk mostly about transmission grid, so I'll do something different. So I'll present our stochastic model that is computationally efficient, and I'll also talk about grid stress. So what is the equipment that is now stressed by everything we are adding on the grid? So again, just to differentiate myself on the power and energy adequacy, I'll be talking about equipment here. So general context, we're hoping to characterize the state of the distribution network. So we're adding plenty of stuff on the grid. We're adding electric vehicles, they increase the power consumption. We're adding residential solar PVs, they're decreasing the power consumption. And we're coming up with new demand response program. And so we're shifting the load this time. So all of those together, they all have important impact on the power consumption, and their number in terms of devices or programs are highly increasing given the energy transition. So collectively, they're all labeled with the name grid edge technologies or behind the meter devices that's been named just before. So here our objective, and oh yeah, so why this fancy name? So if we picture a traditional power system, we'll have the generation infrastructure. I do not have a laser pointer. We'll have the generation infrastructure on the far left, and then it'll collect the power, send it via transmission system to distribution grid. Now what we're discussing today is everything that is tied to the grid from the customer side. For us modelers, what it means is that everything is absolutely invisible. We have very low visibility of what's going on, and for sure, it involves renewables and people, so it's absolutely stochastic. So what we want to do now is assess the impact on the distribution system. So really much on the equipment of adding all those devices so that we can better assess the system's reliability and ultimately the resiliency. So what I mean by that is if I picture some of those gets like EVs, there'll be a stochastic effect of putting all those EV in this neighborhood or all of them in this neighborhood close to the transformer, far away from the transformer, and so on and so forth. And that's really much what we want to look into. So for assessing the impact of GET on distribution network, traditional approach that has been named this morning would be a deterministic analysis. So let's take a typical or worst case loading scenario, run a power flow analysis, and look at what's coming out of this. That would be great, simple to implement, but yield limited conclusion. Then we can go full-on stochastic and run a Monte Carlo simulation. At this time, we'll sample all our uncertainty. That could be, do I have a probability of placing my EV there, 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 or there? And we'll run every scenario many times, That, again, is simple to implement. Each time I need to run, again, a power flow computation, but this is very much time-consuming. So if I want to test new settings, then that'll take a few hours, let's say. So what I want to present today is our rapid estimation method to do such an analysis. So what does this look like? As input, it'll take a penetration, let's call it P, a penetration rate of a technology, just the number of devices on the number of load. That can be PVs or EVs, and the other input will be the load adoption data. So that's my data-driven part. I'll come back to that on the next slide. The output, what I really want is a probability distribution function. I don't want a single number. I want this kind of bell curve around that is centered around something so I can better plan. And I want this bell curve to model the impact on the grid. Two examples I'll be taking today is equipment loading. So what is the apparent power flowing through this equipment and the voltage magnitude of the distribution grid. So because I want to move away from a Monte Carlo simulation that can be quite time consuming, I'll use another tool. I'll use the so-called Fokker-Planck equation to model the stochasticity of my system. That'll allow me to compute the evolution of the state distribution, so loading or voltage magnitude, as a function of P. So I'll get this knob, the P, the penetration rate, and I can play around with it and see what's the stress I'm inducing to my grid. So let's illustrate that. Oh, no, I want to talk about input data, that's right. So I also mentioned input data, and I don't want to oversee it. So this is where this is my source of uncertainty. What is my data, and how will it influence the system? So I'll need three things that can come from statistical surveys or historical load profile analysis. So three things. Quantity probability, how many EVs and PVs and the associated probability with each customer or each load on the grid. I want to see what's the offset that these devices are causing, increasing or decreasing. So this is represented in my cartoonish figure on the right. If we look at the middle one, the blue profile would be someone, say, that is working during the day, commuting back and charging the whole night with a low-level charger, whereas, let's say, green would be someone that goes and bring the kids to school, come back at home because they're working home, charge a vehicle, go back to run some errand, and charge back, and so on and so forth. And then the last thing I need is an adoption probability. What is my probability of being profile 1, 2, and 3? And that will, of course, depend on the day. So, for example, this kind of analysis can be obtained from a data set from data from AMI, from utilities. And we propose a model that I'd be happy to discuss offline that can infer those kind of EV input data using a data-driven, training-free optimization approach. Okay, now I want to showcase this approach. So I want to analyze one of the distribution system, one of the standard distribution system that has more or less 1,200 spot load, 4,000 customers, and I'll look into two types of gets. First, EVs with different profiles and configuration, and I'll do the same with PVs. So this is very much my favorite picture. So I'll be looking at network abnormal condition. So let's take a step back and think of 20 years ago, very little EV on the grid. So on my penetration rate is at 0. I'll look at some section of the grid that are mildly stressed. Then I'll jump in the future, and I'm at 50% penetration rate. That means 1 out of 2 load has an EV. And so all the selected section that I have a probability of overloading that is above 0. So that's something to consider. If I look at the probability of the line overloading close to the substation, so the substation is the green droplet to the far right of the slide, then my probability is going toward 50. So we'll need definitively to think about that. And then if we look at voltage condition as well, close to the middle voltage regulator, so the middle green droplet, my probability of over voltage also gets close to 50%, which is again something to plan accordingly. I can do the same thing with PVs. Now I'll look at the stress again. 20 years ago, no PVs. We're jumping to 50% PVs. So I guess we're in a jurisdiction that has good sun and weather condition for that. And now all the selected conditions that were mildly stressed at the P equal to 0 now have a probability of overvoltage that almost half have a probability of overvoltage that is above 0. If we look at the section close to the substation, then the probability of overvoltage gets very high, nearly 100%. So Definitively, there'll be some grid hardening to do at this point. Also, close to voltage regulator, again, the green droplets, we have a probability of overloading that increases, so we'll need to take that into account. So just to show off a bit, what does that mean in terms of computation time? The kind of analysis I've showed you, running one time of our method will be around 5 minutes, whereas a naive, unparallelized Monte Carlo simulation would take more like 20 hours. That said, our approach is equipment specific. So if I want to do the full map that I just showed, I'll have to run it for every part of it, but the computation will grow linearly, so we'll still have an advantage there. But something that we would not be able to, that would be virtually very hard to do with a Monte Carlo simulation is I want to look at the stress on my grid as a function of P. So I could sample every P possible, or because I have a semi-analytical form, I can just play around with this knob of P and look at what is the limit my current network can host. So for example, what I'm showing here, the bottom figure is what is the penetration rate at which my probability of overloading will be 100%. This is the kind of study I can do because I'm very computationally efficient. Speaking of efficiency, the other thing I can do next is, I'm not mastering that part. Okay, so the next thing I can do is the extension toward time series analysis. My simulation is not costly, so let's look at what is the consequence of this new loading on my network across a day, across eventually a year. So we have an example here of the same grid, the same test system I mentioned with a penetration rate of 80%. So EVs are pretty popular now. And we're showing the mean of the distribution and the two standard deviation and plus or minus. That's the red and green curve. And we're showing this for the main transformer. So the transformer at the end of the distribution feeder. And we see that we're pretty overloaded. So the mean of our distribution is at 120% loading. So we're very much stressing the system. So the equipment is overloaded, which yields a risk of premature failure and increased operating cost and maintenance. So what can we do with that? What I want to discuss now is demand response, but demand response targeting equipment and not only power and energy adequacy. So let's come up with a mitigation strategy. I want to modify a probability, and I'll comment on the probability aspect of it later on, of charging during peak hours. I want to avoid some of this probability. So my adjustment, let's call it delta, should be such that the equipment usable lifetime is not reduced by overloading. That's my hardware objective. But also my incentive, the incentive I'm giving should be cost effective. I should not go over budget. So what is the budget here? It could come from the loss of lifetime that my equipment is suffering. So let's call this F lifetime be the usage factor. If F is above 1, then we're losing, the lifetime is reduced, whereas if it's equal to 1, we'll have the nominal lifetime. Then overloading leads to higher operating temperature, and then higher operating temperature using some thermal aging model leads to a reduced lifetime. This reduced lifetime can then be translated into cost of shortened life. We can think of annual depreciation and the increased cost of maintenance. So all that together, that gives us a budget. If I can beat that, then it's worth investing in demand response, for example. On a purely cost analysis, it's worth investing in demand response to save on my equipment. So I had to put an optimization problem. I teach optimization in power system. So what I want to design is as follows. I want to design incentives such that the induced change in behavior is, okay, first constraint feasible. My incentives are less than the cost reduction of the new lifetime. Then my new lifetime is a function of my thermal aging model of the loading. But what is my loading? It is computed from a time series analysis, either from the RAM approach, you can guess that's my favorite here, or a Monte Carlo simulation of the new distribution. So if I want to solve that, I'll need to run this simulation, run those computations very often. And so that's one way just to showcase my point that if we want to be able to solve this, then we must be able to run those simulations quite often. So that's one of the advantages of having a very light in terms of computation for the model. So in sum, this problem is bi-level, nonlinear, non-convex, so quite not a lot of fun, quite a lot of work to do. So what we can do is reformulate it and leverage our efficient model in such a way. So we want to still minimize our incentives. We want to be cost efficient. So here I've kind of relaxed the constraint that I want to be cost effective with respect to the initial lifetime. So if I'm able to bring it to 1, then this is an exact relaxation. And then what I'll do is instead of having this at large scale constraint, I'll just say, okay, every equipment of interest will have a constraint that I'll call S bar. Off-peak, I'll be very strict. No overloading during off-peak season or off-peak time of the day, and that can be computed from a closed form solution. And then during S-peak, that's where I'll use my REM method. I'll be able to find, using a dedicated search algorithm, what is the one S-bar, so a limit in apparent power that is just enough that you can use everything you want, but that you will not yield premature aging. So what does that look like in terms of simulation? I think it'll better illustrate my point. So I'll use the same feeder as I had before. I'll run the simulation for 24 hours, 1 hour at a time, and I'll just assume for the sake of simplicity that it's the same day every day of the year. My overloading in this system is 3 to 10. F lifetime normally with this kind of PV penetration is 1.1, so we're losing 2 years of service lifetime, which translates into give or take 50K in cost. So here my electricity price is 35 cents, so I'm guessing I'm not in Quebec, that I can tell. And I'll look into 2 kinds of incentives, reward-based, something similar to what Quebec has for now, and time of use tariff, so a hardware-aware time of use tariff, which I guess time of use would be something that is used in Ontario. So the first thing we can do is compute what is the best reward to bring our loading just low enough that we that our equipment does not suffer. So what we'll compute here is a reward that is of around 10 cents for every kilowatt that is shifted. That will bring my cost close to 19K. And more importantly, that would bring the loading on my equipment. Yes, the mean is still above 1, but not long enough that it'll lead to thermal aging. I can then repeat the same thing to compute a time of use tariff. In this case, I'll have three prices: off-peak, mid-peak, and peak. Mid-peak being my nominal price. Then I'll reward people for charging during night, of course, and then I'll penalize people that are that are charging during peak hours. In this case, I'll still be able to push my lifetime back to 1, and my total cost will be reduced to around 17K, a bit lower because I have 1 more degrees of freedom. I have two kind of reward instead of just 1. So in conclusion, what I wanted to discuss today is the need for readily available stochastic models for energy systems for application in planning and operation. To showcase that and to give an example, I presented our rapid estimation method, the REM, that can perform stochastic analysis to study the impact of EVs and PVs on distribution grid. So I've showcased those efficient simulation on large-scale grid, and then I embedded this approach into decision-making to come up with hardware-aware demand response strategies like reward-based and time of use. So what's next for us for this kind of project? We want to look into more grid hardening. So what are the components within a grid, within a distribution network that should be upgraded to be able to host all those amounts of EVs or PVs and potentially demand response, and we want to do that by embedding it into an optimization method. Thank you all for your attention.
Merci beaucoup. On va donc, suivant ce qu'a fait Julia tout à l'heure, on va passer aux questions. So we'll go to the questions immediately. I had a lot of questions, but it worked very well this morning, so I trust you that you can continue on these questions. Donc, on peut prendre les questions dans les 2 langues. Alors, allez-y. Et si on peut me montrer aussi le Mentimeter. C'est la première session. Est-ce que la deuxième session, is there a second session for the Mentimeter? Oui.
Bonjour. First of all, thanks a lot to all 3 speakers. Ma question est pour Antoine. Le modèle que vous avez présenté a des grands avantages au niveau de le temps de calcul. Je me demandais à quel point c'était spécifiquement adapté aux problèmes que vous avez utilisés, parce que ce matin, quelqu'un a justement parlé de Capacity Expansion Models, a dit que c'était trop long pour justement faire des analyses Monte-Carlo. Donc, je me disais, est-ce qu'on pourrait faire le lien entre la méthode que vous avez appliquée à votre problème, puis d'autres problèmes plus larges, comme par exemple les Capacity Expansion Models?
Est-ce que j'ai tout cassé? Non. Donc, non, c'est un bon point. Donc, moi, ici, je me suis concentré sur les réseaux de distribution, aussi parce qu'on en parle moins, mais à savoir si on peut utiliser ce genre de méthode-là pour s'attaquer à des problèmes plus au niveau du transport ou au niveau de la génération. De prime abord, je ne vois pas de restriction. Ici, c'est vraiment qu'on a remplacé l'espèce d'engin de calcul de échantillonner notre distribution puis faire les simulations par une approche qui est plus basée, qui est semi-analytique. Qui est semi-analytique, on va aller venir chercher quel est l'impact d'ajouter 1, 2, 3 événements. On va quantifier ça. Puis par la suite, on va pouvoir pousser puis s'en servir comme... on va pouvoir résoudre un système d'équations pour voir comment ça se propage. Donc, en ce moment, déjà, on peut penser que ça pourrait s'appliquer dans notre réseau, de distribution, à savoir si on veut aller à une capacité plus au transport. C'est vraiment comment on modélise notre incertitude, quelles sont les incertitudes qu'on va aller chercher. Puis après ça, si on est capable de les traduire de la même façon, oui. À savoir, là, je parle un peu de manière générique, parce que je ne sais pas quelle incertitude on veut aller chercher en tant que tel. Mais si on se dit, est-ce que ça peut être du potentiel de wind turbine, peut-être qu'on pourrait faire le même principe. Mais je pense qu'il faudrait qu'on s'assied, qu'on étudie ça, puis qu'on dérive.
Merci.
Merci. Scott, you have already 2 questions. So I'll go for the easy one first. Do you collaborate with Canadian groups to develop your risk map?
Yes, thank you for the question. I think really the component there is NERC does work with a number of areas. We're planning in a lot of different things, standards, assessments, and so forth. Specific to the assessments I spoke on, those are done through the regional planning areas, and that would be specific to whether it's in a provincial territory or somewhere in the states. But from a regulatory standpoint, we wouldn't really get involved with the planning and the assessments and the inputs that go into whether it's the analysis that's backward-looking, the state of reliability report, or the forward-looking assessments like the long-term reliability assessment.
Thanks. And another one more technical. Are you requiring risk mitigation policies by utilities or as a network more largely?
Yes, that's one of the things we're faced with now. Traditionally in the reliability standard called TPL 1-5.1, I believe, which is transmission planning and system performance, basically a standard for which modelers have to model short-term, long-term, steady state, stability, short circuit, and so on for peak load, off load, shoulders, all those other complexities that you have to deal with. The risk mitigation there is only for specific criteria that's not met in that standard. What we're seeing now and what we're working towards, I explained with the extreme scenarios, is under TPL 1, entities or utilities that operate the bulk power system have to mitigate anything that's a deficiency except for extreme scenarios. The work that we're doing now with heat and cold weather, natural events, gas and electric interdependency, as well as distributed energy resources, if those particular events result in cascading instability or separation of the bulk power system, utilities will have to figure out what the corrective measure is. It's a stopgap type situation in the short term, which could be doing things like shedding load if you need to keep the system stable. It could also inform things like capitalization and then building out of transmission systems.
Thanks. And your work of the 3 of you is at very different level, but one issue is that you mentioned it briefly during your talk, is that electricity is playing an ever-growing role in the life of everybody. So we're more depending on more services than before. How does that change your meaning or definition, for example, of resilience? And I will ask this to the 3 of you. How do you see the challenge of resilience as we are more and more dependent on electricity? You want to start, Antoine? Maybe
Yeah, so I guess the answer that the organizer wants, I think we need more modeling. So yeah, so no, but more seriously, yeah, I think it has a lot to do with modeling. We can only indeed be prepared to what we know. So we need a higher granularity in terms of severe weather event in some region. So an approach to that would be to focus on some regions that are nowadays more prone to such event, and then zoom out and zoom out. I think let's try to tackle the issues we're seeing. I think, for example, there's a growing body of literature in public safety power shutoff for power line or even just wildfires in the United States, and there's a growing interest. So that's perfect. That's one of the extreme weather event that is to be tackled. But now that we're getting more into the insight into the problem, then we can extrapolate and maybe recycle those approaches to others.
Thank you. Antoine Rausi, how do you see the question of resilience in the context of where we depend more and more on electricity?
I would say that there are things, if you can forecast what can happen, so I would not call that resilience. It's more, say, reliability analysis. That is, that if you know what can happen and in which configuration you will end up after, say, a catastrophic event like a flooding, a fire, tsunami, whatever, then this is taken into account, I think, into classical reliability engineering. The way I'm seeing resilience is how can we react quickly to something relatively unexpected. That is that assume there is a catastrophic event and we end up in a configuration of, say, the grid, and we cannot really forecast in which configuration we will end up. So the resilience to me is our capacity to quickly react in such, in such circumstances. And of course, I agree with the other Antoine, is that this requires a lot of modeling.
Scott, since you are also not doing analysis, not only modeling, so what's your point of view?
Yes, from an ERC point of view, we're definitely focused on reliability, and it's a very fine line because if you don't do what is needed to maintain the reliability, then there's a compliance obligation. It could be, either just to, fix it and go on, or it could be a monetary penalty. Resilience is definitely, to use the word that was used in a previous presentation, is dubious. We've been trying to figure out a way to create metrics around it so that we can understand how to measure it and address it. It's, from a definition standpoint, we look at it as the system's flexibility. We want to know how flexible it is to respond to these either incremental or even large changes in the system while maintaining the reliability component, making sure that the energy served and customers don't go in the dark, because that's the last thing we want to have happen. And with all of the complexities that we're dealing with, making sure, one, give an example, the winter storm down in Texas, in the United States, where there was loss of life. We want to not gold plate the system, but we want to make sure that we're providing the energy so that there's no loss of life. And that's a key component that we forget sometimes.
Maybe I can comment some more. So the other thing I want just to add is to have a strategy that is very large, to have numerous strategies that can be deployed. We've been talking a bit about demand response, so demand response 1, 2, but also hardware solution. We've been mentioning smart grid and maybe microgrids to add to the equation many levers that we can pull in terms of emergency. And the other thing is to be fast responding to our decision making has low inertia, that we can address something when it happens instead of having long delay. That's another thing that could be or should be investigated.
Thanks. A question for Antoine Rausi. Did you apply your approach to energy system yet? So we don't hear you.
Okay, that's I had issues with unmuting. We not yet, to be honest. The only preliminary work is the one I mentioned. That is that to optimize the deployment of an offshore wind farm.
Are there, when you look at the energy system, I mean, do you see specific problems from your approach compared with other type of systems you're looking at, or more close to industrial systems? Or
I think the key difference is indeed for energy system, there is already a lot of model out there for a historical reason and technological reason, of course. So where the situation may be a bit different is that I guess the issue on energy system is more to integrate the results you can get from different models into some higher level model. And this is where our approach can bring something, probably. This where I would make the difference compared to other industries in which there are, say, less model to make strategic decision in general.
Thanks. Questions in the room? Vous pouvez encore venir poser vos questions. So let me go back maybe to adaptation. We did not talk about this. Adaptations, there's a global transformation, but there's also the catastrophic elements. So how do you classify these transformation and when you analyze risk, when you move forward? How do you integrate some of these changes, and how do you put them maybe in the way you look at risks? I'll start with you, Scott.
That's an excellent question. I guess from a NERC perspective, since we are a stakeholder-based entity, a lot of the work that we do in terms of characterizing specific risk in terms of what needs to be mitigated is done through our standards development process. We want to make certain that even though we maintain an independence of what gets done and how we do the analysis on things and assessments, when it comes to creating the criteria, we do have an opinion in some cases that from a standard standpoint in the performance that utilities have to perform under, we're not going to make that independently. We're going to do a transparent process where the stakeholders get in the room, the subject matter experts that are experts in their fields like yourselves in the planning world, and work through those details, understanding the probabilities, the complexities, doing the Monte Carlos, what in the planning world needs to actually be considered and studied. And that's one of the things that's a little bit different more recently is this heat and cold weather work that's going on. That particular team has created a lot of questions for me in particular, because I have to understand how to interpret that against the Federal Energy Regulatory Order that came out, the directive, to make sure that they meet those objectives. And as I mentioned earlier, when it comes to questions like, is it appropriate to have loss of load? Can you drop load to keep the system stable? And that's one of the questions we're trying to figure out is that an acceptable level of risk to allow that to actually happen? Can it be consequential, which means it happened because some type of contingency occurred, or is it non-consequential, means something's going on somewhere and I decide to take those actions that Antoine was talking about where you drop demand, you actually take outages, public safety power shutoffs like they do in California. How do you determine what's reasonable and acceptable, not just from a reliability standpoint, but also public opinion?
And Antoine, how would you see the difference, or how do you look at the adaptation, or is it something outside of your...
No, I mean, I like the question. I definitively have to think more about it, but what comes to mind is also having strategies, going back to the same wording I guess I was using, is that can be used for those kinds. So the adaptation comes from the strategy. If we can build strategies that can be used on a daily basis with some benefits, but then they have their own like contingency section that if there's low probability, high risk event happens, then we have a way to put forward some strategy. So if we think of a microgrid could be the one example I have in mind, on a daily basis, it can serve us well, can potentially reduce costs. But then, if there is a public safety power shutoff, it can be it could be islanded and still operate. So it has the resiliency aspect and also the reliability aspect, and also can help reduce the cost of operation and so on. So those kind of strategies that can apply on a contingency base, but also on a more daily would be one of the strategies.
And I see a question here, which on what other options beyond electrification that maybe I will, as the moderator, I will reformulate. As we move to one vector, which is electricity, how do we decrease, or how do we, multiply the diversification or not lose the diversification of energy sources as we move to one vector? How do you integrate this? Because if we move away from gas, from oil, we're kind of limit the vector, which doesn't mean we lose the energy sources. So how do you see this? How do you integrate this when you think about this transformation we're going on?
Wow, that's a lot to think about. That makes my head hurt. I turned off the lights in the hotel room before coming over here to reduce the demand, keep the diversity. At the end of the day, if we think about the traditional systems, they're dispatchable, and we always built to that resource adequacy plan. Figured out what resources you need to meet that one single number, but today you can't do that. And my personal opinion, I don't speak for NERC when it comes to this because we talk about reliability, but just from an energy standpoint, there has to be more engagement from the consumer, and that does get difficult because you have to incentivize things, you have to change perceptions, you have to get consumers engaged, and then you also have to make sure it's equitable.
Antoine?
Yeah, I think I'd go the same way. Finding a diversity within the electrification, so finding in different sources of energy. I mean, that can sound simple to say because not everyone has access to hydro and so on. But I'd add to that one of the research should be the demands of the people and how they get involved in this new problem.
And Antoine Rausi, how is your approach a way to look at this type of questions, or?
I must say that it goes beyond my competence. I may have an opinion as a citizen, but not as a scientist, so I prefer not to answer that.
Thank you. So I see there's no other question in the room, so I would like to thank you, the three of you, very much for your presentation and your discussion. We see the challenge is still ahead of us, and we'll be discussing these issues for a few more months, maybe years, we'll see. So thank you again. Merci à vous tous.